You're listening to the Platform Engineering Podcast, your expert guide to the fascinating world of platform engineering. Each episode brings you in-depth interviews with industry experts and professionals who break down the intricacies of platform architecture, cloud operations, and DevOps practices. From tool reviews to valuable lessons from real-world projects to insights about the best approaches and strategies, you can count on this show to provide you with expert knowledge that will truly elevate your own journey in the world of platform engineering.
Hi, I'm Cory O'Daniel, and welcome to the Platform Engineering Podcast. In the next few episodes, we're going to talk about the history of operations, its evolution into DevOps and platform engineering. We'll talk about the tools, culture, and how the cloud have shaped our industry over the years. My first guest is Mark Burgess, creator of CFEngine, and a physicist focused on promise theory, semantic spacetime, graph theory, and knowledge management. Mark, I'd love to learn about your background and how you get started in computer science and sysadmin, but first I've got to know, have you figured out time dilation? Because you're getting way more done than anybody else I know.
Oh, if only it could keep me young, I would have been happy about that. But no, I haven't figured that one out yet.
Nice. So how did you get started in computer science and system administration?
Great question. Hello, everyone, and thanks for the invitation, Cory. So I was a lowly physicist doing a postdoc. I'd arrived in Oslo. It was my first postdoc after I finished my PhD. And basically the money started running out of the physics PhD, and I had taken over the computing system that we'd bought in order to do the research, which was a newfangled system of Sun workstations back in the day. And over time, I'd sort of gotten my feet wet or my hands dirty or whatever you say, diving into that system and managing it. And as the money ran out of physics, I thought, well, maybe I should look for work in computer science. And one of my colleagues at the time happened to come by and tell me there was a lectureship position in computer science at the university down the road. And I applied and got the job, and the rest is history.
Nice. And so before we kind of hop into CFEngine, for those that aren't familiar, it's a DevOps-oriented platform engineering podcast. But for people that aren't familiar with CFEngine, can you give a short description of what it is and maybe how that role led to the creation of CFEngine, or how you got to the idea?
Yeah, definitely. I mean, it all sort of came out of my being a physicist, right? Because I like to understand things, right? My goal in life is to understand how stuff works, rather than necessarily to build stuff. But as I was sort of diving into the computers and figuring out how they worked, it was taking up too much of my time. And I decided that maybe I could try to automate some of it, having seen some of the kind of scripting stuff that people had done at the university to automate things like monthly scripts to do backups and purge file systems and all kinds of clever things that I thought this is quite impressive. And at the time I was reading a lot about artificial life, and I'd always had this interest in artificial intelligence. And so I thought, what if you could make a kind of a system that would enable me to think about computers as I think about physics. I could study the problem, kind of see what computers do, not what we ask them to do, but actually what they do. Yeah. And then some of it's good, some of it's bad. And if we could kind of select the bits that are bad and filter out those somehow and steer it towards the things that are good, maybe that would be a way to regulate computers as you might imagine regulating a physical system. So in physics, we think about thermodynamic systems, boilers and engines and heat systems and air conditioning and stuff like that.
Yeah.
But computers don't have those kind of regulation principles built in. And I thought, well, they kind of should have those things built in. And if we'd built a system that was stable to begin with, surely it could just kind of fly like a plane on autopilot and correct its minor mistakes. We would just set the course that we wanted, the policy that we wanted it to adopt. And somehow it would be smart enough to consult its sensory stuff and figure out how to steer towards that desired end state and that goal that we wanted it to come out with. So I started to kind of look into how that could be done, and that's what got me on the path of writing CFEngine. I think, people kind of got their expectations for configuration management reset when it became more popular around the cloud, and several of the other systems came out, like Puppet and Chef and Ansible and so on. But my idea, this goes back to 1993, right? This is early days when system administration was fly by the seat of your pants stuff done by bearded wizards with special arcane knowledge and spells and hocus pocus. And trying to turn that domain knowledge into something that could be automated and formalized and made reproducible was kind of a tall order.
Did you see at that point, were you seeing like the same types of resistance from like the sysadmins that we kind of still see in some organizations today as you're like trying to give them this new tool to?
Absolutely. I mean, some people were 100% against this because they wanted their magical incantations to be something that they did and only they could do. But others sort of jumped on this and thought this was really cool, to have a kind of software robot sensing the virtual world inside computer networks and figuring out, where am I, what's going on, how do I rebuild the system in some fancy way. And the expectations kind of changed because systems got simpler as time went by. Yeah? Back in the 90s, there were, 15, 20 different kinds of Unix. It wasn't all Linux. That was really easy to understand. Every flavor of Unix was sort of different, and they had different shell commands with different options. So writing a shell script to do this was a nightmare because you'd be saying, if this is Sun OS version 4.13, then this is the shell command, else if version command, Sun OS version 5, else if this is AIX version, this, it's like a 10 million if then else's just to even say what the first command would be.
Yeah.
Never mind what the kind of desired end state should be. And it seemed pretty obvious that you kind of needed to abstract away all of that variability and turn it into a simple declaration of what you wanted the system to be. And that was what CFEngine was about. And I figured that the system was smart enough to figure out a lot of it by itself. You didn't have to literally declare every shell command and all the options to do it. We could figure that out by kind of, smart, intelligent stuff. So as time went by, this kind of developed into separating out the intent in a kind of declarative way, and then burying the details of evaluating that intent and figuring out the path towards success as a kind of block-solving puzzle like you did in old-fashioned AI with robotics. And that's what I started to do. And I thought at the time, this was when open source Free Software Foundation was just coming out, right? Richard Stallman was looking for new projects, and I thought, well, I can just put this online, let people use it, see if they find it useful. And before I knew it, there were a lot of people using it at CERN and, the particle accelerator place and all of the national labs in the US, Lawrence Berkeley, Los Alamos, a lot of these academics associated with the physics in particular because of my, background.
Yeah.
They took on this thing and started to use it. And then it kind of spread from that.
And what other, so the state at the time, I mean, pretty much everybody was just doing scripting. And that's what we had. We had this very imperative way of describing systems. And it's funny because you're using the word declarative, and I feel like even in my experience, I started getting into operations around 2005 or 2006, and it was still very if based. Like the first time I went into a data center where we were doing any sort of automation, it was still just bash scripts. And I remember we actually built our own that was very similar to Puppet before we discovered Puppet, but even just getting that to the operations team. Again, this is before like the term DevOps is coined. There was just so much resistance and it was so hard. But it sounds like for, at least for you, kind of the network of physicists that are working on these systems where they know that they have to be reproducible. They know they have to be able to be configured, and you don't have time for kind of these things that aren't what you're working on to be slowing you down. Like that was really kind of the boon.
Right. I mean, the other side of that, though, was that at the university, things were very different from your average data center environment today. Like the cloud, we somehow imagine everything should just be the same, right? Because it's easy. It's kind of a stem cell approach to computing. You just churn out a lot of stem cells and eventually they'll differentiate into special things by uploading some software. But back then, at the university, every environment was a special kid. They wanted their special environment. They wanted their own software, their own configurations. Any attempt to standardize would be met with fierce resistance by the academic community in particular. So not only did this software have to adapt to everybody's special needs, it then had to convert those needs into a stable target state, a desired end state that it could converge towards and stay there. Again, like the autopilot idea. But everybody had their own course setting, right? Some people wanted to go to Tokyo, some people to New York, and you had to be able to fly their system in exactly the direction that they wanted it, at the same time as protecting them from themselves against all kinds of nonsense like, garbage collection. It's even today, people never think about garbage collection in systems, right? They will run their systems until the disks fill up, the memory leaks to fullness, whatever we say. And the thing will just crash in the end and you restart it, Control-Alt-Delete, you run the system by rebooting. And as we go towards the cloud, again, this kind of biological approach to systems, just let the things die and then reboot and restart. We're going more in that direction. But back then, computers were much more valuable and much more expensive resources. They couldn't go down. Right? People had it as a matter of pride to keep systems running for years at a time. If you managed to make your system go for a year without rebooting, it was a celebration day. So, times were very different then, and the attitudes towards configurations were very different than the kind of disposable computing that we have today. And so CFEngine emerged in that must never fail environment, can never go down, has to continuously be stabilizing, bolstering, securing, recovering the system in real time against its worst enemies, the users.
Yeah.
Who are constantly trying to sort of crash it in a sense, right?
Yeah. It's funny to think like, that just reminded me, one of my first data centers that I worked in was in healthcare. And I remember the system that I logged into, and it had been up there was a banner when you logged in. It's like, this has been online for 400 and something days. And I remember like the head of ops was very proud of that. And we had to do an upgrade once that required a reboot. And he was like, I don't want to like reset it to 0. But it's funny because compute is a commodity today. Like it is disposable. And the idea of making a service that might be backed by, 20, 30, 40 different containers close to 100% uptime is hard, let alone a single system, like a single operating system or like a single, mainframe. Like that is a world of difference to approach like that kind of uptime.
I mean, I may have had something to do with that kind of shift in the end, because as CFEngine developed, I ended up taking it to the conference circuit in America. The Usenix Lisa conference was kind of the mecca for system administrators back in the day. And after sort of an initial attempt to present CFEngine, which amazed me because it kind of blew me away, because I didn't realize how many people were using it in 1997 when I first went there. But I gave a talk, kind of an academic talk about some of the theory behind it and some of the programming behind it. But in the evening, I gave a birds of a feather session, right, for just interested people. Come along. I'm going to talk about this thing I made called CFEngine. And I rented this little room in the hotel, like for 100 people or something. thinking that if I get a few, that'll be great. But the room was full when I got there, and people were standing outside. They couldn't get through the door. And in the end, I was standing at the front. I was going to show a few slides, and people were literally sitting around my feet. I could barely stand in the room. And I just couldn't believe how many people were already using it, even by 1997. So I actually, it kind of threw me a bit. And on the plane going home, I got sick, as I often do, on long flights. But as I was thinking about how can I explain CFEngine to the academics better, because they didn't really get it. The users kind of could see the utility of it, but they didn't understand this concept of desired state and stabilization and the different ways of thinking about managing systems and regulating systems. So I thought, okay, how can I describe this? And my first thought, because I got sick, was it's a bit like an immune system. And I went back to Oslo and I wrote a paper called Computer Immunology, which I then presented in 1998 at Usenix, still online and still sort of a widely read paper. But I made the point there that actually, in biology, we have a strategy for survival has a lot to do with just disposable technology, right? We've got billions and billions of cells. And if you scratch your arm, a few, million cells roll off onto the floor, but it doesn't matter. We just make a few new ones and we keep going. There's sufficient redundancy to make systems robust. But today, we can't afford to do that because we only have like 100 systems. Back then, it was hundreds of computers. The really big people maybe had 1,000, but then they were really big. And at that conference, it was very interesting. After my talk, some folks from the Sandia Government Laboratory, Los Alamos, I think, came up to me and they said, hey, do you know these guys at Los Alamos? They also have a project called Computer Immunology. And one of the other guys at the conference was Steve Tragot, my friend, who now runs infrastructures.org, and he had similar notions of how to scale systems in production. He'd worked at NASA and other places. Anyway, so got a long story short, this discussion kind of came out about how to balance the notion of throwing systems away and rebuilding them versus stabilizing this valuable thing that you can't possibly throw away or do without. So, and these were sort of competing methodologies for a while, converging towards this perfect, stable state and living forever versus live and let die, throw it all away, go out on the ledge and just do your thing and then make a new one and let the next generation take over. And so when virtual machines came along, early 2000s, then suddenly there was this way of doing both, right? You could have this kind of cellular reproductive approach to throwing away systems, rebuilding them, even freezing the state and transporting them somewhere else and re-energizing them, recovering them from suspended animation, so to speak.
Yeah.
And that kind of took over as it became cheaper and cheaper to do that, and those technologies had to scale really quickly. And so people put more effort into that side than into the desired end state approach. And by the time kind of the end of the 2000s came along, when Puppet and Chef came into the picture, the cloud had definitely got a foothold, and the Googles had taken over, and this approach to kind of throw it all away and rebuild was definitely starting to take over and was eroding that kind of desired state thing.
Yeah, I want to talk about that, but I want to rewind to that room that you were talking about where you had just the entire room was packed full, because we have a lot of startups that listen to the podcast, and I feel like most of them would kill for that experience. Like when that happened, it's really funny. I feel like you always see your first users using your system and they use it in just ways that you would not have expected. And and then that's where you start to kind of gravitate towards these people are using it. When you met this just room full of people that weren't academics that were using CFEngine, were there any surprising use cases or significant reactions that you just didn't foresee people using CFEngine for?
Always. I mean, people never used it the way I thought you should use it. And to this day, they still don't. But But there are a few kind of aficionados who are really good, and they understand all the deep principles. And it does way too much, right? Because I envisaged this kind of whole artificial life system that was monitoring the system. It was doing, like in the 90s, it was doing early machine learning, which by that, almost unheard of in the 90s. And it was monitoring and reacting and compensating and all of these different things together. So some people would use one tiny bit of it and other people would use another. It kind of blew me away that by the early to mid 2000s, you could go literally any computer data center in the world, any small or large, the mega software places like Amazon or AT&T to the smallest startups. You turn over any rock in an IT data center, and you would find CFEngine growing underneath it like a moss. It was, on millions and millions of systems. It was just extraordinary to me. And even today, that version, which was version 2 back then, is still there, running. Again, some of these largest providers who shall not be named are running that old software still to this day. Maybe even just running one script that does hardly anything, but it's still there, which is extraordinary when you think about it. The lifetime is now 33 years or something like that.
Yeah, that is awesome. So as the big, the Googles and the Amazons and like big clouds starts to emerge, like how did that affect CFEngine? How did CFEngine kind of change to meet these, not just configuration management, but now like infrastructure management?
So back then, say early millennium time, 2000-ish, I was very, very active in the research community around system administration. I was the chair of that mega conference in 2001. And so I was involved in a lot of these processes. We had a lot of workshops around CFEngine. Started out as the CFEngine workshop and then gradually became the configuration management workshop, from which Luke Canis emerged and made Puppet and so on. So there's a whole kind of history there. But that story meant that we were all talking to each other and adapting to the changes. My PhD student at the time, Kira Begnam, and his friend John Seacrest that I met at LISA, were very interested in the virtual machines. And I'd be honest, they didn't interest me that much back then, but they were really keen on these virtual machines. And John in particular saw the business potential of virtualization as a way of managing data centers. And so we built an early model of cloud using CFEngine to instantiate machines and to control the processes ongoing on different machines. And maybe not everybody knows this, but CFEngine is designed to make every individual computer be an autonomous entity. It's not a massive deploy and spread one image to every machine kind of system, because it had to adapt to all of these special users. Every machine had its integrity and its autonomy to the point where it was actually impossible to send instructions or destructions to the machine from outside. By design decision, both for security reasons and for autonomy, privacy reasons, basically, people didn't want their systems to be overridden by some central entity. They wanted their autonomy. So that model meant it was less easy to deploy to, say, 1 million machines and decide which one's going to do what and orchestrate all of that behavior. So that required some pretty fancy jutsu stuff to make that happen, which was all sort of developed into the theory behind CFEngine. And at some point, I realized that the original model that I'd had was missing some bits and pieces. And I kind of went back to the drawing board and came up with something which ended up being called promise theory in 2003. 2004 was actually the first time I wrote it down. And that has been, I thought it was maybe something I would do for a couple of months while I figured it out, but it's actually taken over 20 years of my life, figuring out all the consequences of this model, how things cooperate and form systems, everything from biology to physics to computer science to AI and all that stuff today. It's all sort of embeddable within this framework of promise theory, which is just about how things cooperate that are initially autonomous, but kind of have to work together. And putting that story into something that can be scaled was, it's kind of taken over my life.
Yeah. So is that like, it's funny. I read up a bit on promise theory, and I'd love you to kind of give an Eli 5 to people that aren't familiar with it. But it seems like the idea, at least, well, I'll let you give the Eli 5, but it seems like that idea is, especially with the speed at which AI is starting to do many things, whether good or bad, as you were saying earlier, if we just focus on those good parts and filter out the bad parts. But it seems like that becomes almost more important as we get to these systems that can behave on their own.
The whole thing came out of an argument that I had around 2003 with some guys doing network management in Europe. And the classical model that everybody in computer science to this day still uses is that you have to force computers and anything around you to do what you want, right? So it goes back to our manual intervention kind of style. We like to use our hands, get in there, and we imagine ourselves wrestling systems with our hands and turning them into whatever we want by our control. But actually, that's not the way things really work. We need that cooperation to be able to do that. And so people would make systems based on the notion of obligation. We must make the system do this. We must force the system to do that. It must obey our commands. I turned it on its head and realized that what if you can't do that? What if you need its permission to make a change, and it will only cooperate on a voluntary basis with your instructions or your wishes. So I would like you to obey this security guideline. Well, screw you, I'm not going to do it. So there's not much you can do about that. But if you can get the cooperation of the system, you could say, well, I will take the bits that I want and I will leave the bits that I don't, and I will do this and I will cooperate to some extent. So instead of forcing and obliging and making things mandatory, I wanted things to promise what they would comply with or what they would agree to do and behave as. And to build the scaling of systems from that idea that we respect one another's autonomy and we react to one another's promises. So if you won't promise to be a good guy, I'm going to promise to protect myself against you. And that's the way it's going to be. And as a scaling paradigm, that works extremely well because it requires a lot less communication to get on with your own thing and occasionally listen to some hints and rumors about this and that than it does to actually send every single instruction over the internet, character by character and often repeated 20 times a day. So it's enormously wasteful to do that mandatory push-based engineering. And it's very scalable and economical to do pull-based voluntary cooperation. So promise theory is about that. It says, imagine a world in which every agent, every thing, person, machine, whatever, is an independent entity. You can't force it to do anything. It will only promise what it intends to do. So it's a statement of its intent. That declaration of intent that we were talking about in CFEngine, that's the key to the desired state that its lifestyle. It's what it intends to do. And so you have this kind of lifestyle model of engineering in which everything declares its intent to behave in a certain way, and we kind of manage that and corral it in ways much as we do with humans.
And this is something that we kind of pursue, I feel like, as operations engineers, kind of everywhere, like whether it's our secrets management or whether it's compliance around like PII, like we wish we had systems that could actually, make sure that the healthcare patient's social security number is never accessible by a human. But we know that somebody will be able to get around that system. There's a database someplace that somebody can log into and access it. eventually that will be in an application that shouldn't have it, right? Like these are things that we're pursuing today, but we're pursuing them through, I feel like a lot of reinventing the wheel from one technology to the other.
Absolutely. I reckon the reason I worked on this for 20 years is because I saw how powerful this idea was and how fundamental it was, not only to scaling, engineering systems like physics and whatnot, but actually to protecting the integrity of information. And so it has a security story. Obviously, it has a scalability story. But when you get onto things like managing functional adaptations, it also is the root and core of how we make software, right? Autonomous pieces, to the point of view, from object orientation to functional programming. People now make these kind of actor-based things where they're autonomous things and they pass hints to each other to adapt and to, respond in certain ways, keeping themselves safe and integral, but at the same time being quickly responsive without being inundated with requests and so on from outside. So this has been hugely important to a large number of areas that I've ended up working on. And I, in some ways, left behind configuration management years ago now. I left I started the company CFEngine to bring about the latest version CFEngine 3 back in 2008, I think. Some years later, I left, and for the last 10 years, I've been kind of applying that to other things, software-defined networking, data pipelining, monitoring, pardon me, data consistency platforms recently, integration of microservices. Okay, so microservices are another case in point where we want autonomy in small silos. Once upon a time we would say silos are bad, okay? And today we say silos are good, okay? But they don't talk to each other, which is bad. So we need to connect them together and figure out that problem for scaling human kind of workforce. And that has created a whole new level of understanding about how we scale IT systems as not just, not just engineering technical systems, but human technical systems, human engineering systems. Because the bottleneck in a lot of cases are the humans who are maintaining, reprogramming, updating, developing, and so on, these microservices. And in doing the human side, we're often negligent of the human interaction more than of the technical interaction, because a lot of people, feel more comfortable talking to the computer than they do to their fellow men and women. So the promise theory story has also had a kind of a component there where people managing teams and getting communication, the DevOps story, that whole thing has built on this promise theory notion of how do we cooperate by making promises to one another rather than throwing commands and instructions over the wall and obliging one another, forcing each other to do stuff.
Yeah. Is there a practical implementation of promise theory, or is it something that we are just a theory that we should be applying to how we develop software and contracts and APIs? Or is there something out there that you can actually use and wrap around systems?
There are many, right? I mean, the theory as a theory is written down in a book. It's all very mathematical. It has no particular allegiance to computer science or to biology or anything, and it's just general. But then there is CFEngine, which was the first kind of IT implementation of promises. First of all, what kind of language to use to express promises in an autonomous way. So I will promise to do this, cross my heart, hope to die kind of thing, rather than you better do that or else kind of push-based systems. But then you have systems like Cisco made the software-defined networking what was it called? ACL, SAC. I'm terrible with names. I'm sorry. They had anyway. They built on promise theory a kind of first model of software-defined networking, and then there were the smart data pipelines that we built around Aljabra. Was a project, great way to understand cloud-based systems on a higher level, piping valuable data to one another to take care of things in the same way that we, pass data between microservices today. And then, of course, there's your whole API design kind of approach to things. So there are lots of ways we can imagine implementations of promise theory being designed. What I see is, even though I've been hands off for a lot of this stuff, what I see is that more and more systems are following the ideals of promise theory, regardless of whether I had anything to do with it or not. People are just converging around this idea that this is the way we have to build systems now. And one of the first things that jumped out at me about Kubernetes was the initial presentation was basically a promise theory talk. And I don't know whether it had anything to do with me giving a talk about promise theory back in 2008 in Los Angeles, but maybe it did, maybe it didn't. But I see that shift to autonomy also in human teams, right? The Agile Manifesto, Lean, and all of these kind of management ideas are very much about letting people get on with the job, using their expertise, promising what they will deliver, and keeping those promises while communicating on a sort of minimal level to coordinate. So the ideas are very general, and you see them arise again and again. And I hope to see this succeed. I hope that this helps people to solve problems and find the right kind of balance between push and pull and whatnot.
Yeah, and I feel like with the rise of AI, it's funny. I feel like when we first started seeing the chat GPTs of the world, the thing that people were saying early on was that it would automate the way that we interact with APIs. And then you see everybody trying to use it to write code now, which I feel like it's not quite nailed. I feel like it's missing a bit of the picture. Like it's got exposure to code, but not the experience of running the code, right? And when we think about writing software, at least I personally find some of the lowest value development time when I'm using somebody else's API, right? I have a business goal. I have something that a user wants to do, but I'm working with this API that somebody has developed because they're trying to expose a system to me, right? And so to think about where AI is going, to be able to have these systems that I can focus on what this thing's purpose is and what it can and cannot or will not allow others to do. And these systems just kind of interact with each other. So I can say there's Stripe. I'm not going to try to read the docs and implement everything and get an implementation wrong. These systems should just be able to behave together. And it seems like that will be really important as AI starts to take over maybe some of the way that our systems interact. We want to be able to wrap these guarantees around it. But I do see it, you see it in Kubernetes. I feel like we see the idea of this, whether we know the term or not. We see engineers trying to do this today in almost all of our systems and operational software.
I see a strong resistance in IT towards kind of learning from the past. We're not very good at passing on knowledge from generation to generation. And part of it is because the technology itself changes rapidly and is such a learning curve to keep going that it seems somehow less of a challenge to just make something yourself than to absorb the knowledge from the past. And I think that's going to hold us back to some extent. And anyone thinking that AI is going to solve this for us is kind of fooling themselves. Because knowledge is not something that you can put into a system for you to do for you. It's something that has to be very much in your mind as you are interacting with it. There are these sort of wiki systems that companies buy to store company knowledge.
Oh, yeah.
I'll not be named. And I often joke about them saying that they're data graveyards. They're places where knowledge goes to die. And what you often find is that people will write a document. How do we install a new user on our system? They write the document. It goes into the wiki thing. And no one ever looks at it ever again. They figure it out the hard way the next time, and then they write their own document to help the next guy. And no one looks at that document ever again. And so there's this growing amount of waste that we never go back and look at. And in a way, the entire academic literature follows that pattern. We write down some lessons that we've learned, and no one looks at them more than once or a couple of times. And generation by generation pass, and it's going pretty fast now. And we lose the lessons that we've learned. In a way, I feel, a little bit honored that Promise Theory has survived some of those machinations, to the extent that a few people at least remember it and talk about it. And at least the ethos of it survives, even if the name doesn't, or, who came up with it doesn't matter. But my dream has always been that this would permeate the industry somehow, and people would run with it and go with it and use it for good. Hopefully it will improve systems and allow us to solve problems we couldn't solve.
Yeah, and like we mentioned at the top, knowledge management is one of your focus areas. Can you tell us a bit about some of the work that you've been doing in that space?
I mean, when I started the CFEngine company, I didn't think we'd be able to sell configuration management as a thing, because it was free, right? It was open source. Everyone was already using CFEngine 2. Again, literally moss under every stone in every data center. But then came Puppet and Chef the year after, and they were supported by these VCs. And I thought, well, maybe there is a story. They had some customers, so people buying this stuff. I was amazed, but why not? So we had to go. That's how the company started. But, my thought was, we already know how to configure systems. What we don't know is how to understand the monster we've created, especially as we got this enormous systems, thousands and tens of thousands and millions of machines after a while. It's easy to set something up, but as it evolves and degrades and misbehaves or whatever, how do we understand that? How do we keep it on track? We can't possibly keep it in our heads. So the machine needs to do some of the work, hence the AI connection, hence the machine learning connection. But again, the fierce resistance of engineers to adopt those automation methodologies has kind of held us back. And what we've ended up doing is, instead of mastering the scaling through technology, we've divided up the scaling into small pizza teams, everybody dealing with their small system, and everybody managing, an interaction, a symbiosis between a bunch of developers and a bunch of containers, which never scales beyond a few, dozen boxes. And that people can keep in their head. This is the opposite of what I anticipated back in 1993, where I thought, the machine will take over and we'll just kind of interact with it as we do other technologies today. But people valued their own expertise and saw it as a game, right? I believe many IT workers are gamers. And for them, solving problems is like killing dragons on the command line. They would much rather figure out this perfect jutsu move with all the backslashes and minus options to some shell command to make something happen by magic than they would ask some AI or some automatic system, please figure this out and solve it for me. Because they want to have the honor of having done that and prove their skill to their coworkers. And that persists, it's shifted away from sysadmins now to developers. So developers are doing a lot of those things, whether they like it or not. Many of them don't.
They do not.
It's kind of been forced upon them, right, by that method of working. And it's evolved out of that need to scale the human management task rather than the technological management task. Interestingly, there are still some of the old users of CFEngine, pure systems like, I think I'm allowed to say LinkedIn because they never hid that from anyone. They only had like 5 engineers running their entire world operation, and they did it using CFEngine. 5 people could scale millions of machines. That was the idea back in the day, because there weren't that many skilled people. But now it's kind of shifted more towards that pizza team model. And I see that definitely the way things are going. And so there's scalability challenges, and the communication and cooperation challenges also change. Now you never go to an IT conference without 90% of the conference almost being about IT guys saying, how do we make friends? How do we talk to each other? How do we form communities? How do we hold each other's hands and be good to each other? Because they know how to do the tech. They can build things on a penny, but they don't know how to talk to each other as human beings and cooperate and solve those human challenges of working together and productizing things and serving one another and being a good service industry in a way.
Yeah, it's funny because like when you look at, there was a report, there's a state of CD report, and they kind of, one of the things they measure is like the adoption of infrastructure as code configuration management. And it's actually a terrifyingly low number. It's like 27% of respondents, right? Like it's not, and it's probably like not 100% rolled out in most of the companies these people are at, right? But it's funny when I have friends that I would consider, gray beard or older school operations people who resist this idea of community and using tools like CFEngine, Terraform, Ansible, et cetera, to codify their expertise. And the wild thing is, at the same time, like we've always had this like joke 10x engineer that recruiters kind of throw out, and operations people truly, if they lean into community and building software to reproduce systems, they're the only ones that can really be a 10x engineer. Like they can actually force multiply and make other teams way more efficient. And I think that a lot of them have a struggle acknowledging that. Like you can, not necessarily we're trying to all amass power, but like you have a lot of power in being able to share your knowledge, not just hoard your knowledge. And I feel like a lot of them think like, well, if I automate me, I don't have a purpose here anymore. And it's like, no, you do. You have your continued expertise on how this system behaves in production.
Absolutely. And going back to your original question, which I kind of lost in my diatribe, apologies.
I'm the same way.
My research has been about how to represent knowledge and how to write it down in a way that allows it to live in people's heads and not just in some database, right? Because the worst thing you can do is put it in a wiki or a database and let it die. You need to be getting it out and looking at it. Right now I'm learning a language, a new language, and you understand the importance of practicing and rehearsing and using and thinking about how to apply the language when you try to speak something, when you're trying to make use of knowledge. We don't often think about that in response to IT or technical skills, or when we go to school to learn physics or something, we don't try to apply it every day. We'll be happy to consult a book after a few years and see if we can pick something out. But really active knowledge, something that on a day-to-day basis is useful to us, that requires keeping it in your mind. This actually led me to apply promise theory in a different way, something that became known as semantic space-time, where you can sort of imagine a view of the world in which every volume in space and time has some kind of function, has some kind of message or purpose. It's solving a problem. It's like the table in front of me is holding my glass up. It has the purpose of holding things up. Whereas the shelf is for storing books, obviously, and the computer is for doing this and that. And everything sort of keeps a kind of promise, and we organize space and time around us in order to be functional in that way. And this is how everything from ants to human beings sort of adapt the environment around them to create this kind of symbiotic accelerative process around us. And, I've spent a lot of time talking about how this works. I wrote a book about it called Smart Space-Time, which I wanted to write in order to bring more people along on this journey of understanding how we get from very basic ideas about organizing stuff all the way through understanding physics and biology to AI at the end, with a very small number of basic principles that come out of promise theory. Everything's an autonomous thing. You offer something, somebody accepts it or not, and you make that work, or you don't, and you kind of evolve that point of view. It's the basis of Darwin's evolution. Things offer their random mutations, and they're either selected or not by something else. It's offer and accept. It's this contract idea between autonomous entities. It's not under any grand control. It's sort of an emergent thing. And yet it's the basis on which all of our complex systems have come about. So I do feel we've got a long way to go in understanding how to make these things work. We tend to run after the latest shiny object in tech, because it's cool. But figuring out how to put all this to the benefit of humanity is something we still don't know or understand very well. I was in New York probably 20 years ago now, well, just as the cloud was coming out, and I had a fierce argument with a good friend of mine, about the cloud. He thought, the cloud's going to take over everything. It's so cheap. There's no argument against it. And I said, well, it's not going to be cheap forever because it's so easy, so good. It's going to end up being expensive, right? The supply and demand. And he said, no, it's going to take over. And I think, well, eventually people will go back to their small systems again. And I think we see that now, things fragmenting, people walking away from cloud back to on-premises systems, because not only the cost, but the mental cost of coping with that complexity is hard. And the reason we've built microservices and pizza teams and so on is to protect humans from having too much to cope with. The machines can do it. It's we who can't do it. And that's why we scale things in small cells. So we have this cellular, again, the biological model. It's creating new cells, new organelles, new organs, which we recombine on different levels. And this is the way we need to understand smart spacetime as the technological basis of our next level civilization. These huge sort of number crunching things like the ultimate AI, not going to happen because we won't want it to happen. We don't want them to replace us, and therefore they won't. We will scale them back until they help us and make us better life forms independent of one another, because we value our autonomy too much to let it go.
I definitely agree. I think AI is one of those things that if you think it will replace you, it will, and if you don't think it will, it won't. And I think that's the distinction there, is realizing that you can use this thing as a tool to make yourself and your team better versus how will I compete with this. So we're getting close to the top of the hour. I would love to know. I mean, it's funny. I feel like every few years we don't necessarily learn from our past and we recreate the wheel in the way that we've managed systems. We've gone from data centers to VMs to containers to serverless containers. And we're about to see this big shift to systems that may or may not be managed by AI. What advice would you give to current or aspiring DevOps and system administrators trying to become more efficient and become a better member of their operational community?
Read my books, damn it.
There will be a link in the show notes for sure. I just ordered it yesterday.
Okay. That's number one. Obviously, number one, the most important thing of all. But read books, because there are so many ideas out there. And, the way I get my ideas is, I reckon on any scale, I'm sort of a cross-disciplinary person, whether it's coming from physics to biology to computer science, whatever. It's true because I read a lot and I have a lot of ideas at the same time. And so I'm working on three things at the same time and I end up kind of putting them together. And that's what leads to innovation. So read everything that you can, understand everything that you can. But maybe the two most important things for everybody to have a good life is be humble and be good to yourself. Because whipping yourself to learn every last thing, or to master every skill, or to work every hour, day and night to produce as much as possible and make as much money as you can. None of those things mean anything at the end of the day as much as your own well-being and your own state of mind. You do your best work when you feel good about yourself. And so taking care of yourself first is always the good thing to do. And being happy is also the place from which, creativity and generosity springs. And again, that's how you make friends. That's how you form good communities. And it's how we end up making the next generation. So, simple answer, right? There's no rocket science to living a life. It's buy my books and be good to yourself.
And be good to yourself. It's that easy. Well, I think that's the perfect way to end the show. I absolutely love it. Mark, it has been wonderful having you on. I really appreciate the time. And
thank you so much for the invitation. I very much appreciate being remembered.
Well, CFEngine started it all. Thanks so much.
Thank you for listening to this episode of the Platform Engineering Podcast. Have a topic you would love to learn more about? Let us know at Cory@massdriver.cloud. That's CORY@MASSDRIVER.cloud. Catch you on the next one.